In this video, we're going to talk about how to do inference for multiple regression using JMP. So let's start by setting up the model. Going back to this home prices data, and I'm going to do analyze fit model because I want more than one explanatory variable. And I'm going to do my price in thousands just because I want to look at the sums of squares, and if my response variable is in like hundreds of thousands, the numbers are just going to be way too big to deal with. So I'll do price in thousands, and then my explanatory variables are square foot and lake, the location. And we're going to be talking about this output down here, including the effect test, so if you want to pop that one out. So the first box is just the summary of fit. I'm not going to write anything down for that one because it's exactly the same as it was for simple regression. So R squared is telling us the proportion of the variability that's explained by the model, and that's referring to the whole model, so it includes both size and the location variable. And then the root mean square error is telling us how large our residuals are. So this is saying that on average, we would expect our predictions to be off by about $72,000 if we use this model. So now let's get to the inference part. We're going to start off with the analysis of variance table. So this analysis of variance table, this is for testing the overall model. So in the analysis of variance table, it's not broken up into the part explained by size and the part explained by location. It's just looking at the whole model together. So the null hypothesis here is not that just one of the slopes is equal to 0. The null hypothesis is that both of the slopes, so the slope that corresponds to size and the slope that corresponds to location, are both equal to 0. In other words, neither of those predictors is helping you, neither one of them is associated with the price. So this is like saying your model is basically useless, right? If all your slopes are 0, it doesn't matter what you plug in for x1 and x2, it all just goes away and you end up with your intercept. So this would be testing a null hypothesis that your model is totally useless against the alternative, which just says that at least one of your slopes is different from 0. So at least one beta, could be beta 1 or beta 2, is not equal to 0. So this is saying that at least one variable in your model is useful for predicting the price. So this Anova table should look really familiar. We've got degrees of freedom, we've got sums of squares. The mean square is just going to be the sum of squares divided by the degrees of freedom. And then for our F ratio, we're taking the mean square for the model. This is the whole model that includes size and location, and dividing that by the mean square for the error. And when we do that, it comes out to be 62.1516. So if we wanted to use the F distribution to calculate the p-value, we could do that. We would just use the degrees of freedom for the model, which is 2, and for the denominator, the degrees of freedom for error, which is 10, and we could calculate it with the F distribution. But I'm just going to let JMP do this for me directly. So it tells me that my p-value is very, very small here, less than 0.0001. And so that tells me that I have very strong evidence, right? And we always say strong evidence against the null and for the alternative. So in this case, this would be very strong evidence that at least one predictor, so that could be size or location, that at least one of our predictors is associated with the price. So at least one of them is useful for predicting price. And right now we don't know which of them is actually the useful one. Maybe they're both useful, maybe it's just one or the other. So we always start off with using the Anova F test for the collective effects of all the explanatory variables. And the reason we do this first, instead of jumping straight to the individual test, is that we don't want to have an inflated type 1 error rate from doing a bunch of individual tests at the beginning. So we're going to do this first. We test the overall model first, and then if the p-value is small, then we follow up using t-tests or f-tests for the individual predictors. So for the follow-up tests, we can use the values from the parameter estimates table, or we can use the effect test estimates. So notice that right now these are really giving us the same information. If you take the t ratio, like 5.23 as the one for size, if you take that number and you square it, then you get the F ratio. And the p-value for size is 0.0004. It's the same regardless of whether you're looking at the t-test or the f-test. So either one of these would be okay. And what these are testing is just one of the predictors at a time. So this would be testing like beta I equals 0. And I'm just going to put the I there as like a placeholder. So it could be beta 1 or it could be beta 2, depending on which row we're looking at. And then the alternative would be that that slope, that population slope, is not equal to 0. So in other words, the null is that there's no association between that variable and the response after controlling for the other variable in the model. So let's go ahead and state our conclusions. So for size, the p-value we said was 0.0004, so that's smaller than most reasonable alpha levels. And we would say that this provides strong evidence. Right? It doesn't seem like the null hypothesis is a good explanation for the data. So we have strong evidence to conclude the alternative, which is that there is an association between size and price. So to conclude that size is associated with price. But remember, there's always that little tag to add at the end when we're talking about multiple regression, because this is not just looking at the relationship between size and price, it's actually the relationship between size and price after adjusting for the other variables. So in this case, after adjusting for location. And we saw that earlier, how this is not the same slope that we would get in a simple linear regression model, and it's not the same p-value either, because we're testing something totally different. We're testing the relationship between size and price after adjusting for location. And we can do the same kind of thing for the location variable. So again, our p-value is very small. This time it's less than 0.0001, so small that it doesn't even really register. And we've got strong evidence to conclude that location this time is the variable we're looking at. That location is associated with price. So this is a useful predictor of price. And that's after adjusting for the other variable in the model. So in this case, after adjusting for size. And I do want to mention that the effect test that we're using here, the sums of squares are the adjusted sums of squares. So we've seen adjusted sums of squares before. Sometimes that's an important distinction and sometimes it's not. In this situation, it is important to note that these are adjusted sums of squares. Why is that distinction important in this particular example? Maybe pause the video for a second. Think about why adjusted sums of squares are important here. So we only have to worry about adjusted sums of squares when there's an association between the explanatory variables. So in this case, there's an association between the explanatory variables, which is, in this case, size and location. So this tends to happen when you have an observational study. If you have an observational study, you can't design it to be perfectly balanced. And so you end up with an association between your two explanatory variables. And that leads to covariation. So in this case, you're going to have some variability in the prices that could be explained by either of the two variables. It could be explained by size, or it could be explained by location. So I'm just going to draw a simple little illustration here. So let's let this box be the variability that's explained by size, and I'm going to draw an overlapping box that shows the variability explained by location. So if I think about what's being measured by the adjusted sums of squares for size, basically it's only the unique contribution of size. So I'm not including that covariation, the part in the middle. And I could do the same sort of thing for location. So again, this one is size, this one is location. Sorry, these boxes are getting very messy. But if I wanted to look at the adjusted sums of squares for location, then I'm talking about just this part that is uniquely explained by location. I'm not going to include the covariation in the middle. So then how does that compare to SS model? SS model is going to include all of it. So we've got our size and location. This looks nothing like the shapes of the other boxes, pretend it does. SS model is going to include the whole thing. So the part explained by size, location, and then also this part in the middle, this includes the covariation. So then if we think about adding them up, adding up the adjusted sums of squares is not going to sum up to SS model, because if we add them up, we're not counting the covariation. We're not counting the part in the middle. And so this is going to be less than the total, less than SS model.